I'm Scot Schultz from Mellanox. I manage most of the HPC activities within Mellanox. So thanks for having me. I think we heard a lot today, both in tandem with GTC as well as with here within the OpenPOWER Summit. And really the future is here. And from an interconnect perspective, we're sitting today at a nice pace of 100 gigabits a second, kind of like moving down the Autobahn, but we're not going to stop there, right? We're probably expect to see twice that speed sometime next year. So it really is about, especially in my area of interest, which is high-performance computing, it's all about the ever-growing demand for higher performance, right? That's kind of what we're all striving for, being able to solve our problems in less time, with less resources, lower power, and really the interconnect is the enabling technology on how we're actually moving science forward. So pushing the frontiers of science and technology really will require extreme computing. With machines in the future, as you see out in time, right? We'll be looking at machines that will certainly be up to 1,000 times more powerful than even today's most powerful supercomputers. So technology, it really has had to keep up pace in order to make the kind of levels of achievements and levels of performance that we've kind of been accustomed to achieving year after year or decade after decade. And so we've made notable improvements moving from technologies, say, from SMP to cluster-type architecture. We've added in multiple cores in packaging, so we've moved to the multi-core architecture. We've done amazing things with GPU acceleration and FPGAs and other co-processing type capabilities. And really, what is next? What is the next thing what is the next step in helping us get to what we would consider exascale class, exaflop class type computing? So there's a new initiative going on around what's called co-design. And co-design really is a way to enable the next generation of architecture, not from just a single company type centric view, but as we do within OpenPOWER, and you've heard this all day long, right? It's been a very standard message across the board. Open collaboration is the way to achieve next generation and next innovation milestones within our technology pace. So actually taking a look at the hardware and the middleware and the software and being able to orchestrate all of this together is the fundamental goal, and keeping everything non-proprietary. So things that are based on standards is very healthy. It promotes a faster pace of innovation. And you've heard it time and time and again today. There's not one single company or one single evolution that's able to provide all of the elements that are going to be needed to achieve exascale. So OpenPOWER really is a force and is driving industry innovation through co-design. OpenPOWER and Mellanox is a founding member of OpenPOWER, and it really does enable greater innovation through both the hardware as well as the software. So this collaboration through multiple thought leaders who are very much experts in their areas of technical discipline, companies like Xilinx, companies like NVIDIA and Mellanox and IBM, and there's really not one single dependent or independent company that's going to be able to provide you with all the tools, semantics, the tool chain, software, hardware, everything that you're going to need in order to achieve this level of innovation. So OpenPOWER Foundation really does create this open ecosystem. And I'm sure you're going to hear that message time and again, even before the day's end. Now, from a networking perspective, from Mellanox's perspective, right, we believe that one of the core challenges is really breaking the application latency wall. So today, if you look right front and center of the slide there, you can see that even today's network device latencies are really on the order of hundreds of nanoseconds. In the future, we certainly hoping to slash that in half, as well as reduce all of what's the communication framework overhead that is generated, right? Especially as you scale out, designing massive, supercomputers that have millions and millions of process and active threads trying to communicate with each other, passing messages and whatnot, requires a significant amount of bandwidth. But it's not just about the speeds and feeds. It's about how you actually pass messages and improve the network architecture under the hood, right? So the solution, in addition to co-design, really is, from a Mellanox's perspective, is what we are doing today, which is adding more intelligence to the network. And what I mean by that is being able to basically beef up the network to be able to handle certain types of floating point operations, being able to actually work on the data, not from moving. In the past, we've moved data from point A to point B, and then we started working on it. But that paradigm's really kind of long gone. There's really, from a CPU-centric mindset, where all of the incremental performance in the past has been done from a CPU-centric kind of mindset, where we've optimized drivers, we made incremental performance improvements in the middleware and the application layers. It gave us some performance improvements, but what we really need to do is get to the next order of magnitude of performance, right? Where is something significant going to come into play that's really going to be what power is really all about? And that's, what is the game changer? From a Mellanox perspective, we continue to add more intelligence into the network, fundamentally allowing the network to become an active coprocessor, right? So it's not just GPUs and FPGAs that are going to become coprocessors. We're doing this now today with a product I'll talk to in just a minute called Switch IB2, where we're actually offloading from the CPU the semantics around MPI collective operations. So I talked about ConnectX-4 a bit last year, and of course you're going to see it on the hardware reveal, and you can come by our booth and see it as well. ConnectX-4 certainly has CAPI support. And one of the advantages of power architecture and why Mellanox is very much interested in this is because alongside CAPI, CAPI actually provides this optimized platform for being able to not only move enormous amounts of data, but CAPI really does simplify the memory management and ties closer the interconnect and the CPU. So it provides a tighter level of integration. This translates into reduced latency. You get away from all of the PCI Express semantics. ConnectX-4 is not just a InfiniBand-only adapter. It's a VPI adapter, so it's virtual protocol. You can run either InfiniBand, a native RDMA capability, or you can run Ethernet at 100 gig as well. You can fundamentally take advantage of RoCE and CAPI technology together simultaneously if Ethernet is your choice of infrastructure. So what we announced at Supercomputing, and if you have not heard, but Switch IB2 is the follow-on. It's the second generation of EDR InfiniBand technology. And we basically have really introduced a fundamental capability in here called SHAP. And SHAP technology is a scalable hierarchical aggregation protocol, which is, how did Jeff say this morning, very easy to roll off the tongue type of marketing term. But fundamentally what this stands for is basically allowing the network now to actively participate in the processing capabilities of the system as a whole. So, it picks up all of the attributes of the first generation architecture of EDR anyway. So less than 90 nanoseconds of very predictable port-to-port latency. It's not a range of 90 to 130. It's actually very predictable latency. 100 gigabits a second, so we can pump about 7.2 terabits a second through this box and handle more than 7 billion messages per second. So for HPC, this is pretty significant. But what is this advantage of the scalable hierarchical aggregation protocol called SHAP? And fundamentally, the key benefit here is that we're able to now move the collective operations to the network. And so the switch is going to be able to handle the operations that would traditionally be handled through multiple network communications. And so if you think of it in the terms of having maybe a 1,000-node cluster, and you wanted to get the results from the process of the threads that are running on each one of these compute nodes, and you send a communication out via one of the collective operations and say, hey, I need you to halt your processing for a moment, and I need to get all your results so that we can start being able to work on the next phase of the problem. This actually would involve numerous network transactions, right, from the node that was requesting the operation. Now, today what we do is basically we send a single communication to the switch. The switch is inherently already connected to all the compute nodes. And so we let the switch actually say, hey, go tell all the compute nodes to halt what you're doing, gather all the results. And when I mean gather the results, we actually gather the results. It's an aggregation type of process, right? So we're going to get all the results from all the compute nodes, and we're going to aggregate that data into the switch and then send that as a single transaction back to the head node. So that's just a very quick example. So what is the benefit of this? This really gets us 10x performance improvement, right? And in some cases, well, I think I slipped a slide there. In a lot of cases, we get more than 10x speed up. So this is one particular example. Mini-FE is an application that's out there. It's used across many RFPs to actually gauge the performance of a system that would be acceptable to solve some workloads. It's basically a finite element analysis type simulation application. And you can see with the graph on the right that just by introducing the collective operations onto the switch, you can see a speed up as you scale out with more nodes. You see a very nice scaling here as far as what the ratio of performance benefit is. And for this particular, now this is just a simulation mini-FE. This is not an actual application. But you can see that for one particular collective operation, which is all reduce, which is kind of what this shows off, you get little more than 25x of the performance improvement, right? So this is really what we're looking for as far as what is the next game changer, right? Now this is very different, conversely, to the alternative type technologies out there like OmniPath, which is all about onload capabilities, right? So that adapter is basically kind of a dumb NIC. It's just kind of a buffer, and all of the processing capabilities is actually handled on the processor, right? So Mellanox's goal is to remove from the processor so that you free up the processor to actually do what you bought the platform to do, and that's to work on your code, not to work on the network communication stack. So with that, I wanted to just also touch, I'm running a little short on time, but I think I'm good with my slides, is also in the hardware reveal, you'll be able to see the end-to-end solution. So there's the SB7800 switch IB2, which we just talked about. And then as well, we introduced, since the last summit, 100 gigabits a second of Ethernet technology over Spectrum, which is 32 ports of Ethernet. So the HCA is VPI, as I mentioned, so it does InfiniBand or Ethernet. But from the switch perspective, in order to actually make it the maximum performance-based switching technology that we can possibly do, we no longer are doing, or at least for the time being, we're no longer doing the VPI from the switch perspective. These are Ethernet or InfiniBand type options. But so with Spectrum, it's also based on Open Ethernet, right? So again, it's a world based on open standards, and that's basically what we totally drive to and what we believe in. But it's the world's only non-blocking, non-packet dropping switch that can function as 10, 25, 50, 100 gigabits a second. It's an awesome switch. It's been reviewed by numerous reports out there and benchmarks as far as the zero packet loss capabilities that you can take on with the Spectrum architecture. And deployment really is actually as easy as creating, instead of creating or buying a very bulky, expensive chassis-based switch, you can fundamentally put this in what's called a VMS type architecture, which is a virtual modular switch, right? Being able to take advantage of the speeds and feeds. I guess the saying on the Ethernet side, and I'm an InfiniBand guy, but the saying is 25 is the new 10, and 50 is the new 40, and these types of things. So this switch really is an amazing performance based Ethernet switch, and you can basically use the same connectors, the same infrastructure, and get 2.5x of throughput versus what you may have already as an install base today from the enterprise side. That's just about it. My timer just hit 0 as well, but maybe we can just take a question or two, if there is one.